Good afternoon, everyone. Welcome to the final session of today's FTTP. So our resource person would be Dr. Justin Varghese. So Dr. Justin Varghese is currently working as professor in Karpam College of Engineering, Coimbatore. He received the Best Paper Award at IEEE International Conference on Advanced Computing. He has published 58 research papers in international journals, proceedings, books, and many other ISI, SCIE indexed journals. He has presented in over 15 IEEE international conferences, including those conducted in India, Italy, and KSA. He also serves as reviewer of many reputed journals, including IEEE Trans on Fuzzy Systems, Industrial Electronics, IEEE Signal Processing Letters, IET Image Processing, and LCV Signal Processing journals. Presently, he is a co-investigator of a major research project funded by DRDO, Naval Research Board, India. His research interests include signal and image processing, visual perception, mathematical morphology, digital watermarking, fuzzy logic, and pattern recognition. Over to you, sir. Thank you.
Thank you. Very good morning to all of you. Okay. Before starting the session, I feel my sound is audible to all of you. Okay. If there is any problem, you can just comment. Am I audible to you, my student, my faculty members? Am I audible to you?
Yes, sir.
Okay. So the topic which we are going to cover today is the binary search tree and AVL tree, and also the implementation of binary search tree. So let us straight away go into the topic. Okay, hopefully you may have some introduction on this. Okay, so the basic definition of tree, everybody know, it is a connected acyclic graph, which means there should be a connection between, there should be a path between every pair of vertices, and there should not be any cycle. What is a cycle? Cycle means, cycle in a graph means a path starting and ending at the same vertex. Okay, so that should not be there. It should be like this. Okay, so this is an example of a tree. So let me. Sorry. So tree, I told you, the connected acyclic graph. Okay, so that is called a tree, and connected means with every pair of vertices there should be at least one path. Okay. And then what I will see is there should not be any cycle. So cycle means what in the graph terminology? It is a path starting and ending at the same vertex. So coming to the other definitions. Okay, so I feel it is the PowerPoint is now visible to you. The tree is a finite non-empty set of elements where they are arranged in a hierarchy. So, and of course, it is a non-linear data structure. Okay, it's a non-linear data structure. It does not provide any linear structure like array, conventional array. So this is what tree definition. And when we go, now I'm not going to the basic definitions of tree node, what is a leaf node. I feel you are all familiar with these basic terminologies, and we are just rushing towards binary search. Okay, so that is what we are going to do. We want, so what is the degree of a vertex, all these things, all you may have completed in the preliminary classes, right? So a tree can be represented in two ways. One is the linked list representation, and which is mostly preferred, okay, because of the effective memory usage. Okay, and then the other implementation, we use the array representation. So, for example, here you can see that here you use two self-referential pointers. Okay, one is for the left child and another for the right child, and then you have the data. Okay, and since we use the self-referential structures, this kind of data structures are called self-referential data structures. Okay, so This is one type of representation, that is a linked list representation. So when you take the tree, it can be classified into a general tree or a binary. Okay. So in the case of general tree, can contain n number of child, okay, and what you call n number of children it can contain. But specifically for binary tree, you can have at most two children, which means any node can contain what you call two children, one child, or even no child. That is not a problem. Okay. So let me make a binary tree. Binary tree means, what is the definition? At most two children. Okay. So you can take only maximum of two children. Whether it can contain one child, two child, or no children. Okay. So this is what the basic definition of binary. So binary tree is a tree where a node can have at most two children. Okay. A node have either one child, two children, or no children. So the basic structure which we use, it is what you call, we have two self-referential structure, self-referential pointers. So that is called, one is the left and another one is right. What you call, respectively pointing the left child and the right. So for example, if we take this node, it has a data field which is equal to like 8, the value 8, and then it has a left child pointer and right child. So this is the structure. Okay. Preliminary classes you may have come across doubly linked list. Okay, it's almost the same structure that we use here. Say for example, there also you have two pointers. What are the pointers? Can anyone tell me? What are the pointers you use in the case of doubly linked list? You have the address of the next node and also the address of the previous. This here is somewhat similar to that. Here we have the address to the left child and address of the right child, and we have the data. Okay, and all together we call it as the node. So this is the structure of a binary. Okay, and this is a typical example of a binary. Okay. So in binary tree itself, you can have majorly three types of special cases. One is called the full binary tree, which means every parent should have exactly two children, which means no parent can contain a single child. Okay, so which means every parent node should contain exactly two children. Then you say that that kind of tree as full binary tree. So perfect binary. So in the case of perfect binary tree, okay, no, so each level it has to completely fit. Okay, say for example, a binary tree which every internal node has exactly two children and all leaf nodes should be at the same level. Then you say that it is a perfect. Okay, it's also a full binary tree, but perfect binary tree is not always a okay. So now let us go for the complete binary tree. When you say complete binary tree, it has to fill in the what you call level wise order. Say for example, if you have one node, it is no, this is a single node. Suppose if you want another one more node, here again, no problem. Okay, here it is not a problem. Okay. So then next node will be here, next node here. Suppose similarly, it has to fill in the, suppose this K is not there. This is not a complete binary. Understand? So there should not be any gap in the level. Say for example, it has to be filled from left to right. Understand? Without any gap in between. In that case, you say that it's a complete binary. Okay? Hope you understand the concepts. Once you understand the concept, let us go for the binary tree traversal. Okay? So in the case of binary search tree, we have the binary search tree traversal is very much important. So binary tree traversal. Okay, so for any graph, you can traverse in two ways. you can traverse breadth-wise, and also you can traverse in the depth-wise. So which means whenever you say a cross-section, say like this, suppose if you want to traverse the node like this, what you call, come to the depth and then going back. Okay, so if you go or follow a vertical type of movement to visit the nodes, then you say that it is depth first set. Suppose if you want to visit in the level-wise order, then you say that that kind of traversal as breadth first. Understand? So vertical traversal or horizontal traversal. If we go for horizontal traversal, you will call that kind of traversal as breadth first set. But if you move in the vertical direction, then you say that kind of traversal as depth first traversal. Okay. First of all, traversal means the process of visiting or printing the individual nodes or individual node values of a tree in a specified order. We call it as the traverse. Okay. So now let us see the traversal types. Okay. So let us go and open a page. Let me. So hopefully it is visible to you. So let me make it. So say for example, suppose if I have, let me copy one tree. So let us take this. Here what happens is, I already told you there are majorly two types of tree traversal method. One is called the breadth first search, and another one is called the depth first search. Okay, I told you if you try to visit the node in the horizontal fashion, that is the level-wise fashion, then you say that that kind of traversal as a breadth first search. But if you move in the vertical direction, something like this, vertical direction, then you say that kind of traversal as depth first traversal. So in the case of depth first traversal, you have majorly three types of depth first traversal. One is called your reorder traversal. Okay, so pre-order traversal means what you have to remember is you will first visit the node, correct? Then what you do is you will move to the left, and then what you do, you go to the right, correct? So this is what you have to do. Okay, so what at any node, what you have to do is, so let me take 3 copies of it. So it will be here. So what I have is, whenever you have say suppose you are here, right? So what you have to do is you have to first visit the node means what you have to do, you have to print it. What is the value of that node? It is A, correct? Now what is the next option you have? You have to move to the left. So you have to move to the left. So that is what you have to do. Okay, so you are moving to the side. So you will move to the left, correct? And by keeping the right as the pending one. So what you do here, you will make the right movement pending and you will move to the left side. Okay, so you reach that node B. Correct? Now, when you reach that node B, once again you have to follow the same strategy. What is that? Visit left and right. So first option is visit. Visit means what you have to do? You have to print the node. Correct? Now you printed this. Then what are all remaining? Left and right. Okay. So you can do only one option. So now in that case, what you do is you will move to the left by keeping the right pending. Correct? So you will keep the right pending. Correct? So here also one right pending, here also one writing. So you reach here. Once again, you experience visit left and right. Visit means what? Visit means you will print the node. Okay. And then what you do, you have to move to the left. So when you move to the left, understand? So you come here. So you reach that here. And here what you have to, you move to the left. What is pending here? It is the right move. So here you have the right aspect. So now you reach here. Okay, so now reach here and once again it is visit. So visit means so A, B, D, and then what you have is the I. Correct? Now what you have is any left here, no left. So there is no option. Then any right here, no option. So only what is now what we do is we are just backtrack. So you are coming back to the previous because once you have seen the end of the vertical direction move. Okay, so this is I already told you BFS always makes the vertical movement, whereas BFS makes the horizontal movement. So now here, what is pending here? Right. So right means what you have to do is you have to demark the right and you come here. What is that? It is once again visit left and right. So visit means what? Visit means you have to print the data. So what is that? J. And then any left, no right. So you will go here. Now here what is pending? It is right movement is pending. So you are deleting it from the start and then you are coming here. What you have here is visit left right. So visit means what you have to make here? You have to print the data. So what is that data? That is F, correct? So now this is also finished. Now what is remaining here? It is R. So the right movement here in the root node is empty. So that you have to make. So and then you are moving to the right. So what you do? You are moving to the right. Correct? So you are moving to the right. So now when you move at here, what do you have to do once again? Visit left and right. So visit means what you have to do? You have to print C. Okay. And then what you have to do is you have to move to the left. Move to the left means so here you will come. Understand? So you have reached at this position by keeping the right movement as pending. Correct? So here it is pending. So now you reached here. Okay. Any left here? So the straight option is visit. Visit means you have to make it as G. Okay. You print it, print the data G. And then what you have to do is you have to move to the right. Okay, no left, so only right movement here. So K is there. K you have to print the data. Correct? So now this is also finished. Now what is pending here? It is the right. So it is the last data. It is no left, no right. Okay, so only the print option there. So this is the order. Okay. So this is what it is called the pre-order traverse. Clear? Pre-order traverse. Which means the order is visit left and right. So whenever you come to a node, the first option is visit and next option is move to the left by keeping the right pending in the right movement pending in the stack. Okay. So this you have to do. The second type of tree traversal is in order. Means here only difference we have is left, visit, and so here also you have to do the same thing. Okay, so let me make here. So what is the first option you have? You have to move to the left. Move to the left by keeping visit and right pending. So what are pending here? In this case, visit and right. So you reached here. What is the option? Left. First you have to move to the left, then visit the node and then right. So we can move to the left by keeping the visit and right pending. Correct? So visit and right here pending. So here also when it comes, what will happen? Visit and right pending. So you reach that this node. Any left? No left. Next option is visit. Visit means what? You have to print I. Then what is what? This is finished. And now the next option here is you have to, the pending work you have to do. You have to make the visit. Visit means what? You have to print D. Correct? Then what we have is, what is pending now here? It is move to the right. Move to the right means what? You just no left, visit J. Visit J means just print J. Then what we have is no right. So here what is pending? That is P. Okay, so P you will be printing here. And then next option is right. Right means F. That is no left, visit F. Okay. So it means you have already finished what you call these two pending operations. Now you have to do this. What is this option? It is visit. Visit means what? You have to print A. Right? Now you have to move towards the right. Right? So you reach that this place. What are the options you have? Left, visit, and right. So which means what you have to keep pending here also? Visit and right. So visit and right means kept pending. You move to the left. Okay. So here also what you can do is visit and right pending. You cannot now move to the left, no left. So visit only. So what we have to do is we have to print G. Correct? G. Okay. And then move to the right. Move to the right means what will happen? K will be printed. Then now what is pending here is visit. Visit means what? It is C. Okay, so you have to print C. And finally you have right. Right means you will come here, no left, visit only. Everything is. Understand the order? Clear or not? I feel it is clear to you. Similarly, you have the third option, that is the post order. Okay. So in the case of post order, only thing you have is it is left, right, and then this. Understood? So this is the order. So what you have to do is first you have to move to the left by keeping the right and visit. So here also what will happen? The right and visit will be pending. So what will happen here is also visit and right. No, right and visit. Okay. But now you reached here. What will happen? You reach no left, no right, only visit. Visit means I will be pending. Now you have to move to the right. Move to the right by keeping the visit option alone pending. So what will happen? J. J will be printed. No left, no right, only the visit option is pending. So what is the visit option? That is here. What is pending now? It is P. So P is also finished. So now what I have to do? This visit is already finished. Now here it is right. Right means what will happen? You have to print F. And what will happen? Visit. Visit means what will happen? You have to print B. Here. Now you are going here. Okay. So you have the pending option, that is right. You come here. What will happen? Once again, you have the right and visit option pending. So you reach at this position. From here, you move to the left by keeping right and now visit pending. So right means what will happen? K. Okay. So you will be printing K. And then here, what is pending now? Visit G. Correct? So this is printed. And now you have to move to the right. What is that? Right is H. Okay. So this is also finished. Now pending is visiting this node. That is what we call C. And then finally the node. Correct. So this is what the post-order traverses. So these three, because you can see that it provides a vertical movement. This is called depth-wise set or depth-first set. So it is moving in the depth, or it is making in movement in the vertical direction. Okay. But level order traversal, so only one PFS traversal we have, that is called the level order. Okay, so level order traversal we have. So in the level order traversal, what is the order? A, B, C, D, F, G, H, I, J, K. So this is the level order traversal. Understand? Clear? So you have to move in the, always you have to move in the level wise. So first it is level 0, then you have level 1 and level 2, level 3, etc. Okay, so this is called the level order traversal. The order is A, B, C, D, E, A, B, E, F, G, H, I, J, K. So this is hope you understand the tree traversal method, and let us continue. So I'm not what you call not going to explain this because I have already explained this. Okay. So let us go to the program. Okay, so what we have is it's a recursive type of movement. So what you have, so that is why I explained it with the stack. Okay. So what was the in order order? It is left visit and. So which means first you have to make the in order traversal of the left by keeping the pending, printing, and then the right. Okay, so here we have a node. Okay, so from this node only we will start our traversal. Whenever you find that the node is stem, what you do, we will just make the empty. Otherwise, what we do, we will make the, this is the base case we have. Whenever we find a null, we will not print it. So otherwise, what we do is we will make the same traversal that is not given as the order. In order traversal means left, visit, and right. So you have to first make the traversal in the left and then print the data. So what is the data? So that is the visit option. And finally, you have to move to the right. Okay. So you have the pre-order traversal. So pre-order traversal here is the simple thing. So what it is? First you have to pre-order means what? Visit left and right. So visit means A. Then it is B. Then it is C. So here we have already made it. Okay. So there we have explained this. Using the paint. Okay. The post order operation, it is left, right, right. Okay. Okay. Or what you call post order or traversal means what we laid, it is left, right, and then finally this. Okay, so which means first you have to move to the left. That is, you moved at this place. What will happen? There is no left. No right, only visit. So B. And then here, what is pending? Right and visit. So first you have to move to the right. There is no left, no right, only visit option. So B, C, A is the A. So, and let us, and the pseudocode, now I already told you it is left, right, and visit. So first option is you have to make the post order traversal in the to the left child recursively, and then you have to do it in the for the right child recursively, and finally you have to print it up there. Okay, so this is what. So first you move to the left. Okay, once this full left option is finished, you move to the entire right option. Once that is finished, you visit the no. So this is the strategy of post order traversal. These three are depth-wise traversal, which means what three of them are vertical traversal. So that's why it's called depth first search. Okay. And finally, we have the level order traversal, that is the level-wise traversal. So that is horizontal movement you have. So this we simply make it. So what we do is the program here. Okay, so the implementation program here. Okay, all the program we learn at the end of the lecture with the implementation of binary search. So now here what we have is say the function name we here is print level order. Okay, so we have a node. From that node only we are going to start. Okay, so what we do is we have a queue as well as we have a temporary node. So the temporary node for initially we initialize to root. So what we have to do is the algorithmically or how we will do. So let me feel the theory. I feel it's okay for you. Okay, so we already have one example. So the idea here of the program is, say for example, you start at the root, okay, and then what you do is you create a what you call a create a queue. Okay, so what we have is okay, so A we have visited, so make A as visited. The idea of here is A visited. Then what you do is you enqueue the children of B and C to the what you call the queue, right? So now B and C are in the queue. Now what you do, you dequeue the, so here which one is out now? That is B. Okay. So B, then you visit it. Okay. And then what you do is you enqueue the children of B and B. That is B and F. So what are the children here? You have B and F. So you enqueue. Now what you have to do? You have to dequeue the C. So what will happen? C, you have to dequeue it and print it. Now, once you dequeue it and print it, and then what you do? You have to enqueue the children of C. So what are the children of C? Here, the children of C are E and H. D and H. So now what is the next step? Just to dequeue the element. So here it is D. So D, you have to make it here. Then what you do? Okay. So D. What are the children of D? That is I and J. So what you have to do now? You have to enqueue these elements. So what are they? I and D. Correct. Now D to F. So what is this one? So you have the option here. F. Then what you do? What do you call F? No children, no nothing to enqueue. So what you do? You dequeue the G. You print it. G have one child. So what is that child? It's K. So K you make it in the queue. And then you dequeue H and print it. Now H is okay already. It doesn't have children, so you will make I, and then J no doesn't have children. Okay, so it will come as this. So this is how it is practiced. So you can see the program now. So it's very simple. While temp node, which means the temp node until it becomes null, what you have to do is first you have to print the node, the data, whatever it is, and then what you do, you have to enqueue the left child as well as right child if they are not null. Okay, so if temp node arrow left is not equal to null, then what you do, you have to enqueue the left child. Okay, and similarly, if there is right child, you have to enqueue right child also. This process should be continued until the queue become empty. So that is why, and then what you do, we will dequeue the queue, which means the front of the queue will be stored in the temp node. If it is null value, which means what is the meaning? There is no element, you will stop, and otherwise you will in the last. Okay. So what are the things you have to do? First you have to print, then you have to enqueue the left child, then you have to enqueue the right child, then dequeue the element from the front of the queue, and then once again you have to. So this is the implementation of this. And then in sometimes we have to find out the height of the what you call a particular node. Okay, so height of a particular node. So what you have to do is, the idea here is, say for example, suppose this is a node. Suppose the node which I have is, okay, so here what you have is height of a particular what you call uh, node, we have to make it. So suppose I want to find out the height of A, means what I will do is, until it become null, so first it will call the recursive code as what you call the height of, it will find out the height of the left and height of the right. Okay, and then you have to find out the maximum height among this, which means what is the formula, recursive formula we are using here? Say for example, say let me make it very simple for you. Say h of A, I want to find out the height of A, which is equal to, what it will return is 1 plus maximum of what you call, maximum of what you call the, if they are not null, that is also there, the height of the what you call left child, and say for example h of left child B and comma, height of. Now what it will do? It will once again call the, height of B, okay, and height of C. So height of B, what is height of B? It is 1 plus. So what will happen? It is equal to recursively 1 plus. Okay, it is not equal to, B is not null. If it is null, it is 0. Okay, if it is null, it is 0. Otherwise, it is 1 plus. Say now it is not. That is 1 plus. What will happen? Okay, the maximum of, okay, here also. So this height of this one is already here. Okay, so already one maximum here. Okay, sorry. Here it is already maximum. Okay, and I feel I will take more time. Make it little faster. Say maximum one step I will write, and then remaining step you try to the 1 plus here. Okay, so since it is not null, 1 plus what you have is, okay, the maximum of height of what you call B, okay, height of B, comma, height of H, height of F. So this is one thing, correct? So this is for this maximum. And now what we have is, we have another maximum, correct? So here also you have to make it as 1 plus another one. So it is H will call. So what is that H? Is height of, uh, uh, height of, what you call is B, okay? So here it is C. So it will maximum of height of G, 1 plus height of G, comma, maximum of this was H. H is what you call its left child, right child, and null. So it will, what will happen? It will remain 1 and 1, 2. Here, similarly, one more level it will go. So it will be 1 plus 1 plus 1. So this is how recursively this logic will. So now let us see the program. If you have doubt at the end, because we have to keep up the time. So I'm going little faster. So what do you have to do? What is the procedure? If it is, we have program, we will discuss at the end after finishing. So temp is equal to null means what is the meaning? If the current node is null, what do you have to return? You have to return C. Otherwise, what do you have to return? You have to find out the maximum of the left height and maximum of the right height, and then add one to it. Okay. So that is, if left height is greater than right height, simply you can make the maximum. For left height is greater than right height, which means left is having more depth. In that case, add 1 to it. That is the final result. Otherwise, you add the right height. Okay, understand? So see here, for example, in recursive this way, it will determine the height. Say, for example, the height of this, here you will add 1, 1, 2, 3 here. Okay, here the height is 1, 2, 3. So both of them are same. So you will get the answer as 3. Yes. Understand? Clear on. So recursively you do. So this is how you will find the height. Okay, if you don't understand, just ask. So what are the steps? Simple step is, if the current node under consideration is null, you have to return 0. Otherwise, you have to find out the maximum height of the left subtree and the height of the right subtree. Whichever is maximum, you take it, add 1 to it, you will get the height of the subtree. So now let us go for the binary search. Okay, so whenever you go for binary search tree, the basic property we have is, let me say this. So let me, so, and let me go to the, so what we have is binary search. Because binary search tree means it's a binary tree in which every node in a binary search tree have a property that all elements in the left subtree, so if you take this node, all elements in its left subtree are lesser than it, and all elements in the right subtree are higher than. This property has to be followed by each node. So if you take this node, all elements in the left subtree are lesser, and all elements in the right subtree are greater. If you take this node, all elements here are lesser, and here should be greater. Here also it is. Understand? So this is the basic property of binary search. Okay, so binary search tree, I feel you understand, and binary search tree. Okay, so if you not type for BPT, we can use it. So now let us go for the insertion and deletion. So now let us see, let us take some elements here. Okay. Say for example, 15, 21, same. Um, 16. So this is what we have is 17. 17 elements. Okay, so some element. So what you have to do is just let us demonstrate the insertion. So first element to be inserted is 15. So you create a node and you insert the element. Now similarly you have to insert 20. So when you insert 21, what you have to check is you have to check 21 with 50. 21 is greater than 50. So you have to make it as a right check. Okay. So it is here. So now you have to insert 21 as the right check. Now, next element to be inserted is 7. When you compare 7 and 15, what will happen? 7 is lesser than 15. So you have to insert the element as the left sub. So here it is. So now I have inserted it. Yeah. Now it is 16. So 16 means what will happen? 16 and 15 are compared. 16 is greater. And then you move to the right. So there it is 21. 21 and 16, what will happen? 21 is, no, 16 is greater. So what will happen? 16 is lesser. So what will happen? So you will insert it as the left hand. So here it is 16. Clear? Now what we have is 2. 2, what will happen? 2 is lesser. While comparing 7, 2 is lesser. So you insert a known as this as. Now, next element, hopefully you know this. Okay, so you can do it easily. After 2, 3 elements, I'm going to go to the next topic to finish our. So now 7 here. So next element to be inserted is 1. 1 is once again, it is 7 here. So 1 is lesser than 2, 1 is lesser than 15, 7, no, 1 is lesser, 2 is lesser. You have to insert this as the left. Okay. So 1 we will insert here. So now 7, okay, what data we have? 17. 17 is greater, okay, so 17 what we have is 17 is lesser, so here it is 17 is greater. Hopefully. So we have to connect it. So next element, 21 is already there. So yes. So 24 you have. Twenty-four is greater here, so here and I feel it is more than so now it is 13. So 13 means where it will be? 13 is here. So let us finish here. Finish here. So it is 13. It is 13 here and 22 here. So let us only 23. for simplicity. So up to 30. So now this is the insertion. Okay. Now let us go for the deletion. Deletion means there are three cases. We will discuss in the PPT also. So the first case is one. What we have is if the node to be deleted is leaf. Okay. So leaf node means what you have to do, you have to delete it straight. Right? So suppose if I want to delete the node, say for example, here it is 17 or 1 I want to delete. 1 I want to delete. So what I can do, first I have to check where is 1. So first 1 and 15 are compared. So it is lesser. So I move to the left. 7 and 1 are compared. So I move to the left. So 2 and 1 are compared. It is here. And now what I do is I will delete. Okay. Straight away. So this is a leaf node. I'm going to straight away delete. Correct. Now the next option is the next case you have to follow is is 2. That is, if the node to be deleted having only left child, okay, left child or right, okay, only one child, okay. Say suppose if I want to only one child or one, supplement. So any case, any particular case like this, say for 16 here, only one child. So what you have to do is you can, what you call, just make the connection like this. There are two types of implementation. One implementation is copy 17 here and delete 17 from this, and then repeatedly, if there is a tree, that is also you can do. Otherwise, simply what you do is one simple methodology is so you make a connection from here to here, and then what you call delete this. Okay, so this is the way you can understand. Only one child means that child you make the connection with what you call the parent of it. You will literally delete the other one. So delete. Okay. Now the case 3. Okay. 3 means the node has both left and right. Okay. The node to be deleted has both left and right children. So in that case, what you have to do is we should either say, for example, suppose I want to delete 15. So what we have is the node 15 have left child as well as right child. So in that case, you have two possibilities. One is you can replace this element by the maximum of the left subtree, which is the in-order predecessor of the left child. Okay? So which is the in-order predecessor, or you can replace it with the minimum of the right subtree, that is the in-order what you call successor of this. Okay, so you can take two options. What are the options? Either here you can take the maximum of the left, it can replace it by the maximum of the left subtree, or minimum of the right subtree. So which one you are going to take? Let us make it the minimum of the right subtree. So what you have to do here is you have to first delete this. Okay, not delete, just to replace the value only with 17. Okay, which is nothing but the minimum of the right subtree, and then you have to delete 17 from right subtree. Okay, So when you delete 17, this comes in the first case. That is the leaf node. What you can do, you can you can straight away delete it because it is a leaf. Understand? Clear? So these are the three cases. So hope you understand. So go through the slide. Say for example, suppose if I want to delete 16, what I have is, so 66, what I have is, I will make a connection from 70 to this one. So replace. So here is only one track. So this is a 65 degree balance. So the pseudocode for it, what it will do is, first you have to find out the element. Suppose so from a root node, it may start. So we will make it as node, and then the element to be deleted. So what will happen? What will you do? Say for example, this is the insertion operation. So what will you do? If node is equal to null, at some leaf place when you reach, you make a new node and return the address of the node. And what do? You make the element to be inserted key as the data for your job is finished. Otherwise, what will you do? If it is not null, what do you do? Beware that the insertion operation in a binary search tree will only happen in leaf space. Okay, it won't happen in the root space. Okay, so or any parent level, it will happen as a leaf child. So whenever you have an element to be inserted, you have to find out traverse until to the null position where you can add a new node according to its value. So if the value to be inserted is less than the root node value, then you have to move to the left. So what do? If key is less than node, the key of the node, then you move to the left and insert and patch it. Okay, so node arrow left is equal to insert node arrow left. Comma. So you move to the left. Suppose if it is greater than, you move to the right. So that is why node arrow right. So recursively it will make the insertion. And this is what it is. We already explained this. So 10, 12, 12 is greater. So we inserted here 5. So this is the final tree. So after 15, just for a sake of example, let us take 50. 50 is greater, 50 is greater, 50 is lesser than 20. So we will set as a child. So deletion also we discussed. So deletion 3 cases, not to be deleted is a leaf. Simply remove it from the tree. Suppose what you have is, if the node has only one child, what you have to do is say, suppose here I want to make 30. So what you can do is just select 40. Okay? Or either replace this value by 40 and delete 40. That's also possible. And another one, the last one, you have to delete 50. In that case, you can either take the maximum of the left subtree or minimum of the right subtree. So here, if we take the minimum of the right subtree or the in order successor of this node, so that we replace 50 by 60 and then delete 60. 60 is a leaf node, so straight away we can. So this is deletion. Okay. So having said this, okay, and then minimum. How will you find the minimum element in a binary search tree? You will find the minimum element, the leftmost element. So what you have to do until it become null, you have to traverse to the left. Okay, until the node become null, you have to move towards the left. Okay, so what is the logic we have? If while current arrow left not equal to null, what you can do? You have to move to the left until current arrow left is null. Okay, when it become null, in this case, say here it is left is not null, here left is not null. Here this case left is null, that time you return the value of the current arrow data. So that is the return data. Similarly, how will you find out the maximum? You have to move to the right until the its right is null. Okay, you find a node, the rightmost, what you call, the element of the tree, that is uh, beyond that particular node, your, okay, right child address will be null. There is stop, and then from there, what you need to do, you have to send the data. So while current arrow right not equal to null, what you have to do? Current, you increment to current arrow right, and then once you find that the node's right pointer is null, then you return the data. So that is the rightmost element is the greatest element, leftmost element is the smallest. Any other operation? Let's see. Find the maximum. Okay, so we will find, some of the disadvantages also. So what is the major disadvantage for binary search tree is no, it is not a self-balance. Okay. Its worst case time will be order of n. Okay, so what will happen is, suppose if I want to insert elements like say 1 from 8, 21. So what will be the structure it will follow? It will follow structure like this. Okay, all right. Okay, so here you have 1, here you have 4, here you have 8, and here you have 21, and it is correct. So what will happen if you want to search 21? What will happen? You have to first search here, then search here, then search here. But suppose in this case, this is somewhat balanced. So what will happen? Suppose if I want to find 13, so what I have to do first, I will come here, 17 and 13 are compared. 13 is less than, so you will move to the left subtree, and 7 and 13 are compared. 13 is greater, so you move to the right subtree. At that place, you find 13 there. So the computational time for this one, searching 13, is order of log n. Okay, but in this kind of case, if the tree is like this, the computation time is order of n. So worst case is order of n. So that is the major drawback that binary search tree have. So that is why we will go for the AVM tree that we will discuss after finishing the implementation part. Next slide. Okay. The code, you can get it from the coding module. I can share with them. So I already told you. So we have what you call 2 libraries we are including. Okay, and the structure we, while discussing the class itself, we discuss this. Okay, so here what we have is, we have the data field and the self-referential pointers left and right to indicate the left child and right. Okay, so and then we have a root node that is temporarily it is null, and then temporary variable one we have, and the del node also we. So we have 3 variables here. At times comes now what purpose we are using that. So first is in order traverse. We already discussed in order traverse. If temp not equal to null, if temp is equal to null, you do nothing. So that is the, here it is void. It's okay. So that is why we want to return anything. So what we do is we ignore it. Okay, that's otherwise what we do, we will move to the left, then this is in order. In order means left, visit, right. So in that case, first you have to move to the left, then after finishing the left of complete nodes traversal, then you come and print the data or visit the data. And once you make this, you move to the right. So this is why. And pre-order means, what is this? Pre-order means visit left and right, which means at first you print it, then you move to the left subtree, and then after finishing the traversal in the entire left subtree, you will go for the right subtree. So that is why pre-order is a recursive function. We already discussed it. So this is post order. Post order means, what is the order? Left, right, and then finally visit. So post order of, first you move to left, then you move to right, and finally you make the. Then we study the function height. So height, what I told you, how to find out the height of a particular node. So here the height start from 0 to 8 is means made it as that minus. Otherwise, you can make it as 0. Okay. So a single node height means it is 0. Okay. So now what we have is, okay, whenever it is finding it is null. Okay. So what you do is you will find the maximum of left subtree height and right subtree, and then add 1 to it. So you find out the height of the recursively, you find out the height of the left subtree, and then you find out the height of the right subtree, and then you find the maximum. If left subtree height is maximum, is greater, then you add 1 to left subtree height. Otherwise, you add right subtree. And finally, you reduce 1 because the root node height we take as 0. So 0, 1, 2, 3. Now insertion, that also we discussed. So insertion will happen only at the leaf node level, where you find a nodes left or right, a nodes, current nodes, or what do you call here, it is temporary nodes, left or right, what do you call it is, what do you call null. Okay, so that time what you do is, so we'll create a what you call new node using this. So malloc function with the size of structure node. Okay, so we create a node and then we will make the fill its element to the data field to the given element to be inserted, and then make its left as well as right to null. Okay, so theoretically I can discuss this if you want. Okay, after finishing a real tree also. Okay, then we can discuss this. And otherwise, if it doesn't have null, what do you have to do? You have to recursively find out the leaf place. So for that, if the element is less than the data field of the temporary node, then you insert the element in the left subtree. Otherwise, you insert it as the right subtree. So this you have to complete until what you call you will find. So at the other case, what it is, if it is less than, okay, else if what you call, if it is greater than, okay, if it is equal means what is the if element is already exists, which is no not allowed here. Okay, so this is the insertion, and finally we have the searching. Searching how to find out. If it is equal, what you can do? You can return. So if it is null, what is the meaning? Element is not present. So you can return null. Okay. Otherwise, what you do? If it is less than, what you do? You search the element in the left subtree. If the element is greater, you search it in the right subtree. If it is not less, not greater, not null, in that case, what it will be? It will be the element itself. So what do you do? Okay, you return the position of it and stop the position. And after finishing this, what do you do? Even no, that is that. So the return temp. That is what it is. Clear? Then basically null means at this case, what you have is it will return only null only. So we are already up. And then minimum. How to find out the minimum? I told you. Minimum is the leftmost child. Minimum is the leftmost child. So until you find a node where its left is null, until that time you have to move to the left. So right temporal left not equal to null, you have to traverse the tree towards the left. Temporal left. So you have to continue this until a node you find and its left position is equal to. And finally, you just print the data. Okay. So next is maximum. So you move to the rightmost. So only thing instead of left here. Okay. So then it is depth. Okay. So depth also you use the same what you call method. Okay. So here what you do is temporal data equal to element, so you need to make it as 0. Otherwise, what you do? The same 1 plus that you do. Okay, so these are the things which we have. Okay, so clear it is, and it is the driver program we have. Okay, so having said this, let us go for AVL tree for 10-15 minutes. Okay, so 4:15 or 4:20. Or maybe 4:25, 4:20, I will try to make it to 4:22. So let us go for the last part of our lecture, which is the AVL. Okay, so binary search tree, the problem I already told you, sometimes when it is in a ascending order or descending order, it has the what you call or the incremental order. If the data is given in the incremental or decremental order, so what will happen? It will form it like a linear structure. So that time, your computational complexity of searching, insertion, deletion, all these things will become order of n. Correct? So that is the drawback of it. So we need a self-balanced tree, which is being introduced by Adalwelsky and Lange. Okay, so that's why it's called AVL tree. Okay. So AVL tree is a what you call, it's a self-balanced tree where one condition is that it's a binary search tree, there is no doubt about it, but provided each node in the AVL tree is restricted with a balance factor of -1, 0, or plus. Okay, so here we have the node balance factors are -1, 0, or plus. So in this case, what is balance factor? Balance factor means it is a height of the left subtree minus height of the right subtree. So which means balance factor will tell you how much long a tree is slanted in one direction. Okay, if it is 0, that it is correctly balanced. If it is -1 means one step this side. If it is -2 means one step in the left side slant. So understand. So if it is -3 means 3 step it is slanting in the left, no, right side. Okay, so that's what. Say for example, balance factor here. So what is the balance factor here? Here how much? This is 1, 2, 3. So here it is 3, 3 level. Or you can make it as 1, 2, 3. Correct? Here 1, 2, 3. So 3 minus 3. Height of the left subtree minus height of the right. So here let us take here 1, 2. 2 minus, here it is 1. So 2 minus 1, it is 1. Here what is it? 0. 0 minus, here it is 1. So this is how we will find out the balance factor. In the case of AVL, the allowed balance factors are -1, 0, or plus. Okay. So one step slanting, it is not a problem. Okay. So it should not be completely slanted. So when you insert, the insertion operation is same as what you call your binary search tree, provided after insertion you have to check the balance factors of it. Okay. So that is whether it is violating or okay. If it violates, or it means that at some place you find that it is +2 or -2, and accordingly it still run -1 or +1. Okay. In that case, you have to make appropriate arrangement called tree rotation, okay, to make it balanced. So that is why it is called as a self-balanced binary search. Okay, so before going to the exact cases of rotation, so let us go what exactly is rotation. Okay, so majorly, okay, so when you call single rotation, okay, so double rotation, I will tell you it is a combination of two, both the rotation in different ways. So let us make the single rotation now. What will happen is, suppose Because what we have is, suppose if you want to apply left rotation at this node, so any node here. So what happens is, okay, its left child, you are going to make the right rotation. Right rotation at this place means what will happen is its left child will come in its position. So left child, another left, what is the left child here? Is P. So P came here, and then the corresponding node where you applied the rotation has now become the right child of its left child. Now the left side, the node where you apply the rotation has now become the right child of its previous left child. So which means simply here Q has become the left child of the right child of P. So Q has become the right child. And then the right child of P has to be now the left child of Q, which is the parent. Okay, so the right child, so V now should be the left child of Q. So these are the two things. Understand what is it? Suppose if this is a parent here, this parent node will become the right child of its left child. And also what will happen is the right child of the left child, it will now become the left child of the parent. So that's what it is. Understand this? The adjustment here. Okay, so simply we just write here, say for example, P has to be true. So what you have to do is here it has to be the first thing you have to make it is simply making it has to be P. Okay, so and what will happen? The Q will be the right child of P. So what will happen? That you mark. It is same as this. But still for simplicity, just okay. So Q has to be that is the already Q was the parent. So now here Q has become the right child of P. Okay, so if you apply rotation here, okay, if you apply rotation here, it will change. So now, and whatever you have the right subtree, okay, which is correspond to the P, should be the left child or left subtree of what we call the parent node here. That is so here it should come as remaining all will be same. Okay, remaining all are same. They won't change the structure. Either it's A or C, it will not change the structure. Similarly, when you make the what you call the left rotation, what will happen? Which means you apply the rotation here. So you apply the rotation here. So what will happen is this Q will become the pair. So let me make that also and then okay. Okay, so let us make it. So P will be, that is when you apply rotation here, so what will happen? Q will come. Okay, clear. And then the next step is P will become the left child of Q. Okay. P will become the left child of this one. And what will happen is left child of Q. Okay, so left child of Q. What is that? P will be the right child of P. So that is the remaining odd is these are the two single rotations. Remaining elements, say what will be here? It will be A, here it will be C. So that is the understand. So these are the two things you have to remember. And then double rotation means any combination of single rotation. Okay, that is left rotation after right rotation or right rotation after left rotation. That is called double rotation. So now let us go and see what is what you call. So this is the left rotation here. So what will happen? Okay. So what we have is here we have. Let us come to the cases. So insertion operation I already told you. So what we have what you call is the first thing is you have to insert the elements similar to binary search tree, and then what you have to do is you have to check the balance factor, and if any place you find that is -2 plus 2 or something, okay, that is allowed is only 0, 1 and -1, that time you have to do appropriate rotation. So now let us see the four cases. The first case is called the right case. Right case means if the parent having a balance factor of -2 and its right child having a balance factor of -1. Okay, so let me go and take it for you. So this case here, the parent has a balance factor of -1 and its right child has a balance factor of -1, which means the tree is slanted in the right side. So you have to perform the left rotation at the parent. Understand? Parent having any parent, that parent having a balance factor of -2 and the right child having a balance factor of -1, you have to perform the left rotation at the parent. So you will make the left rotation. What is the left rotation? It says 2 will be the parent and 1 will be its left child. Okay, and here there is no element. If there is would have one element, it would have been the right child of X. Clear? First case. So what is the first case? Right case. What is the right case? Any parent is having a balance factor of -2 and its right child is having a balance factor of -1. In that case, what is the remedy we have to perform? We have to perform the single left rotation at the parent. Yeah. Okay. So next case is in this right left case. Okay. So let us see what is right left case. Okay. Next case is right left case, which means any parent having a balance factor of -2 and its right child having a balance factor of +1. Okay, so which means the tree will be somewhat, it will be like this. So here you have -2 and here it is 1, which means first you perform, okay, the right rotation at the right side, that is 3. Here you have to perform the right rotation. So what will happen? It will become like this. Then you have to perform the left rotation at the parent. So what will happen? When you make the rotation here, what will happen? When you make the rotation here, what will happen? It has come like this. So it is the first case which we discussed. Now make the rotation here. So that is the right left case. Similarly, you have the left case. What is the left case? Parent is 2, left child is +1. And left right case, what is that? Parent is having +2 and its its left child having -1. Okay, so in that case it will be like this. Parent having 2, its left child is -1. So first perform left rotation at the left child and then perform right rotation at the parent. Left rotation, when you do it, it is like this. When you make the right rotation, okay. So the other case, left case, what you have to do? Just opposite to this. Here we apply the, this is the case. So this is the case. Okay. So here what we have to do? This is 2 and this is left. You have to apply right rotation at the parent. So now let us see one example and we will finish today's lecture. So let us see. First, I'm going to insert 0, correct? So what will happen? Insert what you call 1. So insert 1 is 0, balance factor is 0, that is height is of the left subtree is 0 and height of the right subtree is 0. Now here what we have is the height of the left subtree is 0, 1, 0 and height of this is 1. No, 0 minus 1, it is minus 1. 3, but allowed. So 0, 1, minus 1. Here when you insert 3, what happened? Parent, here it is left side, it is 0, balance factor 0. Here it is, how much it is? 1, 2. So 0 minus 2, here it is minus 1. Which case this is? Right case. What is the right case says? You have to apply left rotation at the parent. So what will happen? It will make the rotation here. So, yes, so this is after insertion. Now you have inserted 4. Any problem? So here it is 1, here it is 2. So 0 minus 2, it is minus 1. Here also minus 1, minus 0, no problem. When you insert 5, what happened? Once again, the same case. Minus 2, minus 2, minus 1. Which is the case we have minus 2, minus 1. So here only we have to apply the, this is also once again, it is the, which case? Right case. You have to apply left rotation at node 3. That is, node 3 is the plane. So what will happen? Now 4 will become here and 3 will become the left child, remaining on this case. Here we does not have left child of this, so remaining on. So this is what AVL3. I'm just winding up. Okay. Okay. So if you have any doubt or something, you can ask. Anybody having any doubt on this topic to discuss? You can start. The time is almost 9:30. 4:30.
Thank you so much, sir. Professors, if you have any doubts, you can ask Justin Varghese, sir. I hope they don't have any doubts, sir.
Okay.
Thank you so much for the session, sir, for spending your precious time with us.
Okay. Thank you.
Thank you.
Also,
Sir.
thank you for giving me this opportunity to share. Okay. Thank you.
Thank you, sir. Thank you, sir.